for this stupid presentation thing was springs. So we're going to be covering like pretty much everything you know about springs. Springs are actually pretty simple. There's really only, like when you're going to get a spring problem, it's pretty much either going to be about Hooke's law, which is usually just like plugging in numbers or solving for forces on an object attached to a spring, or an energy question, which you've probably already done many energy problems. The only difference is that you have a different equation for potential energy when you have an object attached to a spring. So anyways, this is Hooke's law. It's really straightforward. It's just the spring force is equal to the negative spring constant times the displacement in meters. And this equation obviously has a negative slope. So like this right here, this is a graph of the spring force versus displacement in meters. And it's obviously going to decrease because of the negative k, and it has its highest value, the highest force value at its lowest displacement, and vice versa. This is the equation for spring force, potential energy of spring force, or potential energy of a spring. It's 1/2 kx squared, where k and x are the same thing up here. So if you do have a situation like we described earlier with the spring and an object, so this is when it's at its minimum displacement, like it's just at rest. If it were to get compressed this way, then it would be at its max displacement in the negative, and then when it's released, assuming no friction or resistive forces or anything, it'll go exactly the amount of displacement you just compressed it in the opposite direction. So that would be over here, the negative maximum displacement. This would be the positive maximum displacement. And this is just a graph of energy versus displacement. This blue line is potential energy, the green line is kinetic energy. Kinetic energy is the same thing as it was for like when you learned your unit about energy. It's just 1/2 mv squared. So obviously, potential energy is going to be the highest at the maximum in maximum and negative maximum displacements because of this equation here. X squared is the displacement. So even if it's negative, it doesn't matter because the square gets rid of the negative. And kinetic energy is going to be highest right here. Not only because it will, obviously because of conservation of energy, it's going to have to make up for the loss in potential, but also because the object's going to be moving its fastest as it travels through its like resting point, and it's going to slow down when it gets to its max, and then like come back and retract.
All right. So this right here is a spring at rest, and I'm going to show off how kinetic energy and potential energy work in practice. So if I expand it, its potential energy will increase and increase because the displacement gets larger and larger. But when I bring it back into its resting position, its kinetic energy will be the highest because the velocity will be the highest for the object that the spring is attached to. And then when you compress it all the way, its potential energy again is maximum because the displacement is the largest from the rest.
Okay, so we're doing that problem that we just showed. I just drew a free body diagram just to show you guys like how you would set up a free body diagram, even though we don't really need it for this problem. If you're trying to find like the spring constant, like if it doesn't give you a spring constant, even though it did in this problem, you would set up your free body diagram, and then your net force equations. And this one there's no friction, so the only force is this. So again, that's why you don't need it. But yeah, you would just set up your free body diagrams, and then your net force equations equal to mass times acceleration, the difference in the forces, and then this spring force is always equal to negative kx. So if you have the displacement or the force, you can solve for the spring constant. All right, so for this problem, it gives you spring constant, gives you displacement, it gives you mass. We're looking for velocity as soon as it leaves contact with the spring. When it leaves contact with the spring, we're assuming that's like the instant it happens, so that this displacement is going to be at its maximum, so it's going to be at 2. So we're going to use our energy equations like we talked about earlier to solve for this. So you just want to set it up. So it's going to be like a total change in energy. So potential energy at the beginning of the spring plus kinetic energy at the beginning equal to the potential energy at the end plus the kinetic energy at the end. This is going to go away because at the beginning, when displacement's at its maximum velocity is 0, it's not moving because it's being compressed, so I'm get rid of that. And at the end, potential energy is going to be 0 because it's lost contact with the spring, so this has its maximum velocity, this is 0. We write down the equations for potential energy is 1/2 kx squared, kinetic energy is 1/2 mv squared. And then we have like every single variable we need, so this problem is basically just a plug and chug after that. 1/2 times 300 times displacement is 2 squared is equal to 1/2 times, well, the 1/2s can cancel because they're both on the opposite sides of the equation. The mass is 10, velocity is what we're trying to find. So 300 times 4 is equal to 10v squared, 1200 is equal to 10v squared, 20 is equal to v squared. Square root of 120 is your velocity. So yeah, that's how you do that problem. That was a pretty straightforward problem, but yeah, basically the ways to solve any spring problem, you're just going to want to set up your free body diagram, look for an energy approach if you can. It's just like pretty much any other mechanics problem with you can like do an energy base or try Newton's laws.
Alright, so now we're going to talk about springs in series and in parallel. Now, some of you might know series from electronics, and series is when they're both strung together. One is on top of the other, and when they both hold the mass, it will stretch double as far because the equation is 1/k is equal to 1/k plus 1/k1 plus 1/k2, etc., 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 going on for as many springs as you have. So this, compared to parallel is just all of them added together without taking the reciprocal. So it's obviously a lot stronger. These two springs side by side can hold the same mass, but at half the distance away. So if you're trying to make something a super strong spring, holding a super big weight, you're going to want them to be in parallel because this is able to hold more weight and keep it higher up. But if you're trying to keep a weight further down to the ground, you're going to want to use series because it doubles the displacement. Alright, so some tips and tricks, just to basically go over everything that just happened. Remember that on an oscillating spring with the mass attached to it, the kinetic energy will be maximum when the displacement is 0, when the velocity is maximum, and then the potential energy will be largest at the maximum displacements because it is the furthest away from 0, so it'll go shooting back. If friction is 0, it'll keep oscillating between those 2 points. If there is friction inside the problem, eventually it'll come back to 0. And you want to always remember, if you're given a number in a problem that's Newton meters, it's your spring constant. Always remember Hooke's law is negative kx. Don't forget the negative. That'll mess you up sometimes. And yeah, that's about it.